is German. Yeah, I hope you are able to see the screen also.
Yes, sir.
Okay, great. Where is the... I'll put you on chat so that if there is any question, I'll be able to see. Okay. So I hope the third quiz is released, and it asks you to revise what we did, especially the subset constructions, and I hope you are finding it okay. Yeah, so please do the quiz, because that keeps you sort of up to date with the class material. Okay, so what we did in the last two classes is this operations on languages. That is, given languages A1, A2, we can construct more complex languages by combining them in some ways. For example, we can take the union of the two languages, we can take intersection of two languages, we can even take complement of a language, that is all words in sigma star which are not in A, right? Or we can take catenation of two languages. Now we did this catenation operation, and then the last operation that we partly saw last time was this Kleene closure. Okay, so I hope you're familiar at least up to catenation. Are there any questions on these language operations? And then the kind of theorem that we proved is that if the component languages are regular, that is, they are recognized by some DFA or NFA, then the resulting language, the more combined language, is also regular. That is, if A1 and A2 are regular, then A1 intersection A2 is regular. In that case, we say that regular languages are closed under intersection. That is, if you take any two regular languages, then their intersection is also regular. To prove this effectively, you have to be given two automata, and we have to produce an automaton for the composite language from the components, right? So, for example, the proof method is, given DFAs M1 and M2, we construct a DFA for the intersection. And similarly, we did it for union, we did it for complement, and we did it for catenation. Let me just briefly, we usually is normalized epsilon NFS for this purpose because it's convenient. And here is a construction which takes the union of the component NFS. So, given NFS N1 and N2, which are drawn as R and S, we produce a bigger NFA N3, which recognizes the union of their languages. And we do that by adding these two extra states, S3 and F3, as we saw last time. This is S3 and this is F3, and adding the new transitions drawn here in black. All the transitions of the previous automata are kept as they are, right? So we saw this, and we even saw how this works. We did it for complementation. This was union. So this is the 5-tuple note, the same construction given in 5-tuple notation. Then we defined catenation of two languages. That is, a word of A followed by a word of B. All such combinations are called A dot B, or A catenated with B. And here are some examples we did. And we did also the construction of an automaton which will recognize the catenation of NB. That is, given an automaton N1, which is called R in this diagram, and an automaton N2, both in both are normalized epsilon NFS, we can construct an automaton for language of N1 catenated with language of N2. That is, words of N1 followed by words of N2, right? This is what we do. And this automaton will recognize the catenation of the languages. We saw this last time. So any questions so far? No, right? Okay, so we'll go ahead. Then we introduced a very important operation called Kleene closure, and for that we defined the notion of power of a language. Given a language A over alphabet sigma, we defined a to the power 0 is the set containing only the word, empty word epsilon. Remember, this is not same as the empty set phi, right? This set contains one word, which is the empty word, whereas this set contains no word inside it, right? So that is true. And we recursively define a to the power n plus 1 as we take a, we calculate a to the power n and catenate a with a to the power n. Okay, and here were some examples that we did. So this was done last time. And then we defined a very important operation called Kleene closure, right? And the Kleene closure, what it said was, Kleene closure of A is an infinite union. You take set a to the power 0, a to the power 1, a to the power 2, take all these sets and take their union. So you take union of infinitely many sets, and the resulting set is called A star. Okay, so mathematically you can define it like this and you get it. And we saw this example that if A was a very simple language, it contained only one word AB, right? Then AB to the power AB star will be word AB repeated n times for all possible n's. So you will get epsilon, you will get AB, you will get AB, and like that for all possible number of repetitions of the word AB. That is what you will get. This was one example. We had done some additional examples, and now the question is, can this infinite union be done by a finite state automata? Because it looks like a rather complicated operation, right? You have to do all possible powers and then you have to take their union, right? So here, this we had taken up to power 3, you have to take power 4, 5, take union of all that, and that will give us A star. Now, how do we do this? So the claim is this: given an NFA N1 normalized, we can construct a normalized NFA N2 such that the language of N2 is the Kleene closure or star closure of the language of N1. It will do this infinite union business, just by automaton operation. So, and the construction is given here. Let this box with R, denote the epsilon NFA for N1, so this is its start state is S1, its unique final state is F1. So this is S1, this is F1, right? And we add in N2, we take all the states of N1 and we add 2 extra states. This is called S2 and this is called F2, right? And then we add this 3 arrows which are shown here. One from S2 to S1, one from F1 to F2, and one from F1 to S1. And also, 4 arrows. One also from S2 to F2. So these 4 extra transitions, all marked epsilon, are added, and these 2 states S2 and F2 are added to N1, and the result is what we call as epsilon NFA N2. So is the construction clear to you? Yeah? Let me give an example. Let me give an example of this construction. Suppose your automaton N1 was what automaton? You got one start state. So let us call this as S1. Let us call this as F1. Let us call this as some state P. And on A it remains here. This is an epsilon transition. Sorry, this is. Let me call this as P and let me call this as Q, right? And this is S1. And this is the final state F1, right? And on both A or B, it will go here, and then on A or B, it will remain here, right? This is my epsilon NFA N1. It happens to be deterministic in this case. Okay, sorry, this is not correct. I cannot call this F1. So this I will call this as R. And then on an epsilon transition, I should go to F1. right? Which is the final state. Because I need a in epsilon normalized automaton, I need a final state from which there is no outgoing state, and from the start state there is no incoming transition, right? So do you agree this is an epsilon NFA? What language does it recognize? Anybody? What does it do? It begins with S1 on an epsilon transition, it moves to P. It remains in P till it sees only A's. Then it waits for a B to occur. And if B is the last letter, it can do this epsilon transition and go to the final state. But after that B, if a letter A or B occurs, then it moves to this sync state, reject state, and it will keep rejecting. So basically what language does it accept? All words, you know, where there can be 0 or more A's followed by exactly one B. I mean, I can write this language in short, this notation, A star B. A denotes an arbitrarily many occurrences of A. So 0 or more occurrences of A followed by B. That is the language it recognizes. We could have given very simple automaton for this. We could have just given this automaton, you know. Right? And here there will be A and a B. And this is a partial automaton. Right? So here what happens? This is the start state. Any number of A's can occur, and then if a B occurs, we go to accepting state. And after that, if any more letters occur, we reject. Now this is not really a DFA because we have not drawn any outgoing transition from this state. But this simple automaton is is an NFA. Unfortunately, it's not normalized. Right? So in order to normalize this, I have added all these things. Okay, so in fact, I don't even need to add this part. This is a normalized NFA, which will recognize the same language. So is the language of this NFA N1 clear? And now what will be N2 that we need to, so suppose we want to take Kleene closure of this. That is, we want to find out all those words which can be obtained by repeating this kind of words any number of times. Okay. So for doing that, what do? We add two extra states. So I will draw this extra added states in red. So I will add a state S2 and a state F2, right? And then what will I have? I will have an epsilon transition from S2 to S1. This will become my new initial state. This will become my new final state. This top state will stop being a final state. Okay. And then I'll have an epsilon transition going from here. I will also have an epsilon transition going from this to this. Okay. By this construction, it is this arrow. And then I will add an epsilon transition from F1 to S1. So all these red arrows are the black arrows in the above diagram. So given this automaton, we construct this new automaton, and the claim here is that the language of this newly constructed automaton N2 is the star closure of the language of N1. Whatever the language of N1 was there, we get star closure of the language of N1. So is this clear to you guys? What we are trying to do? Is the construction clear? We will see why it recognizes this language in a moment. But is the construction of the Kleene closure of an epsilon NFA clear? We just have to add two states and add this four arrows, the four red arrows that I have added in this diagram, right? So I think you will all be asked to construct such automata. Huh? Any questions? You can even ask on the chat. Okay, the construction is clear to you guys. How do we give this construction in 5 tuple notation? Well, my N2 is an automaton whose set of states is states in Q1 union these two states S2 and F2. Okay, so two fresh states S2 and F2. We have already said that the start state of the new automaton will be this added S2 and the final state will be F2, right? So that is clear. Now what are the transitions? From this newly added state S2, what are the transitions possible? Well, on an epsilon, it will go to S1 as well as F. Why is this T2? This should be F2. Yes. So you can see that from S2 on an epsilon, you can either go to S1 or you can go to F2. Agreed? So S2 on epsilon goes to S1 and F2 non-deterministically on silent transitions. On the other hand, for on any other letter A which is in alphabet other than epsilon, you don't go anywhere. So you get empty set. This is what describes the behavior of the new automaton from state S2. And for all the states in Q1, you know, on a visible letter A, you do exactly as you would do in N1, no change. On states other than F1, what you will do is on epsilon will also be identical to N1. On F1, there is a change. So on F1 on epsilon, you will go wherever you would go on epsilon in the original thing, but you can also go to S1. This is S1, this is S2, this is F1, and this is F2, right? So you can see we are just drawing this, writing whatever is given in this diagram there, right? So I hope that is clear to you. And that is the construction. And this construction does the job of that infinite union. It repeats the behavior of automaton N1 any number of times. It catenates N1 with itself any number of times, arbitrary number of times. And let us see how it works. So, but the construction should be clear to you, right? And so I will go here. Okay. Oh no, I will need this. So I'm going to have to erase this. Page, delete layer, right? So this is S1, this is F1, this state, this is S2, and this is F2, right? Now the claim is that the language of this is N2, right? And this R is actually N1. Language of N2 is the Kleene closure of the language of N1. How do we do that? For that, we will have to prove that this language, how do we prove two sets are equal? We say that one is a subset of other and the other is the subset of the first one. So first what we will prove is if X belongs to language of N1 star, then X belongs to, what do we have to prove? If X belongs to the language of N1 star, then X belongs to language of N2 that we have constructed. N2 is some automaton we have constructed. Language of N1 is already given to us and its Kleene closure is defined by the closure operation. We have to show that everything which is in Kleene closure is accepted by N2. This is one way. So it will prove that it will prove this, that language of N2 is a superset of the language of Kleene closure of N1. That is what this will prove. So first we will prove this, right? And then we will prove the other subset. Okay, so we are proving in this direction. Right. For that, what do we say? So we say that suppose there is some X which belongs to the language of Kleene closure of N1, right? So that means what? X is of the form. So there are two cases, you know. So let me write this in blue. Case 1. When does a word belong to the Kleene closure of a set? You know, it is of the following thing. It is union of this. So either it is, when does a word belong to A star? Either it is epsilon, that is it belongs to A to the power 0, or it is obtained by, it belongs to catenation of A some n number of times for some arbitrary n. So these are the two cases. Case 1. X is equal to epsilon, right? Because epsilon always belongs to the Kleene closure of any set. In that case, my automaton N2 should accept epsilon, but it does accept epsilon, right? Because you can start from S2 and on an epsilon, you can go to F2, right? So you have a run from the start state of N2 to the final state on epsilon, which means epsilon belongs to language of N2, right? And we have proved the statement when X is equal to epsilon. Case 2 is what? What are the other kind of words other than epsilon which belong to the Kleene closure of a language? X is of the form y1 followed by y2 followed by some yn, where each yi belongs to language of N1. That is language of N1. You pick up different words, maybe same word, maybe different words which belong to language of N1, and you catenate them n times for some arbitrary n. So there exists some n and some subwords y1, y2, y3, yn such that their catenation gives you X, where each yi belongs to the language of N1. These are the only two ways in which a word can get into Kleene closure of language of N1, right? Is this clear to you? Is there any question that, a word in A star can only be of one of these two forms? If X belongs to A star, then either X equal to epsilon because it belongs to A to the power 0, or what happens? X is of the form y1, y2, yn for some n, for some n such that each yi belongs to A, right? This is the only way in which a word can get into A star, and all such words are in A star. This is the defining property of the Kleene closure. So this is the second case that we have got. Where was I? Oops. Where is my... right. This is the second case, right? And what I am claiming is that there is such a word. Now, how do I accept this word X in my automaton N2? Anybody can tell me what kind of accepting run can I generate, which will take me from S2 to F2 on this word X? So I will write that run below. I will start with S2. Then I will take an epsilon transition and I will go to S1, right? That I am allowed to do. Then what will I do? I have got this word Y1, which takes me from S1 to F1. So I will draw this composite notation on this by a sequence of transitions on Y1. I will go to F1. Why? Because I have assumed that each yi belongs to the language of N1, which means what? Y1 belongs to the language of N1, Y2 belongs to the language of N1, which means there is a path from the start state S1 to the final state F1 of N1 on word Y1. So I will mimic exactly those transitions, right? So this notation, double arrow, says that on the sequence of letters Y1, I will move from S1 to F1 with using some maybe epsilon transitions. Is this clear to you? Now from that F1, I will take this epsilon transition and again go to S1. So I will take this epsilon transition and again go to S1. Then I will do a run on Y2, which will also take me to F2. And then I'll do this epsilon transition to S1. I will do like that. Finally, I will have this thing on Y1 from S1 to F1. And then I will take this epsilon transition and go to F2. So you see this constructed run, using runs which are in original N1 on subwords Y1, Y2, Yn. I get a run which takes me from the start state of my constructed automaton to the final state. And hence this word X, which is of this form, is also accepted by this. Implies that X belongs to language of N2. So I hope this is clear to you. If word X belongs to Kleene closure of the language of N1, then it is accepted by language of N2. Maybe N2 accepts many other words. We have not proved anything else. We have just shown that every word in the Kleene closure of language of N1 is in language of N2. Is this clear? Hello? Oops, I'm getting critically low battery. Yes.
We can also prove it using induction on N, right? The number of
Yes. I have given here an informal proof, but actually you can also prove it by induction on N. You're absolutely right. You know, a more formal proof than what I have given would you indeed use induction on N. Give me a second, I need to get my charger. Battery is critically low. I hope we will survive this. Yes, done. Okay. Sorry about that. But this intuitive proof is clear to you. This will work without induction. I mean, you are intuitively saying for every n you can do this, right? Which is technically by induction on n, right?
Yes, sir.
Yeah. Okay. So but the proof is clear that every word which is in the Kleene closure of language of N1 is accepted by N2. Because those words can only be of one of these two forms, and in both cases we have a run, accepting run of N2. Okay, what about reverse? So I will add a page there, new page after. What about reverse? We want to prove that language of N2 is a subset of language of N1 ka Kleene closure, right? Star closure of this language. In the previous proof, we have proved the other way, so, right? So what we have to prove is if X belongs to language of N2, that is X is some word which is accepted by this newly constructed automaton, then X belongs to this language of N1 ka Kleene closure, right? So suppose X is a word which is accepted by N2. There are again two cases. Case 1, right? So how can this newly constructed N2 accept a word? It has to go from, in order to accept the word, it has to go from S2 to F2, because S2 is its unique start state and F2 is its unique final state. So one possibility is that it takes this epsilon transition and goes to F2, in which case it accepts the word epsilon, the empty word, right? That is one possibility. Agreed? So let's first look at that case. You know, case 1 is that it goes from S2 on an epsilon to F2 directly, right? That is, it accepts the word epsilon. But then we already know, but epsilon anyway belongs to the acha. So this epsilon word is getting confused with this belongs to symbol. So I will write it as in language of N1 ka star. Why is this the case? So this shows that epsilon belongs to epsilon in language of N2, right? We are claiming that epsilon is also in the language of N1 star. Why is that the case? Can anybody tell me? What is the definition of what is the definition of A star? Let's go back to the definition of A star. It's A to the power 0 union A to the power 1 union power A to the power 2, etc. Right? So it includes everything in A to the power 0, everything in A to the power 1. Now what is A to the power 0? It contains the empty string. So A star for any arbitrary A will have epsilon in it. Right? Which is why we added this arrow, because epsilon must be there in language of N1 star. So you know, if N2 accepts by taking this epsilon star, we are not going wrong. What is the other case? It accepts by doing what? Any run from S2 to F2 is either of the form going directly from S2 to F2, which is the case 1 we considered, or it grows from S2 to S1, then it goes from S1 to F1, again comes back via this epsilon, goes from S1 to F1 again. It does this some n number of times, and then it takes this epsilon transition and goes to F2. These are the only two kinds of paths which will take you from S2 to F2. So you have to think of all possible paths that go from S2 to F2. So I think the other case is of the following form. You start with S2, then you take epsilon transition and go to S1. Then on some subword Y1, you will go to F1, right? Then you will take epsilon transition, go to S1, do Y2, right? To F2, and this you will repeat some number of times. You know, you will again be in S1, then on some Yn, you will go to F1, and then you will take an epsilon transition, go to S2. So my claim is that all the runs where n is greater than 0, right? So there are only two kinds of accepting runs in my automaton. This is what I'm claiming. Either the run goes directly from S2 to F2, or it goes from S2 to S1, then it has to go to F1, then maybe it repeats by going back to S1 and then coming back here and going back and coming back some n number of times. But at least once it will have to move from S1 to F1, right? It may not take this epsilon directly move to F2. So I have either runs like this or I have runs like this for some n greater than equal to 0. But in this case, since S1 goes to F1, which is an accepting run of my automaton ln1, I get from this that yi belongs to language of n1, right? For all I. And this implies that y1 dot y2 dot y3 dot yn belongs to the language of N2's language, right? Why? Because on this catenation, we have an accepting run. We have this accepting run of N2, which looks like this. Yes, I have this. But this implies, since each yi belongs to language of N1 and I have a finite catenation of words from N1, I also know that y1 dot y2 dot y3 catenated yn belongs to language of N1 star, by definition of language of N1 star. So what we have shown is that in both cases, when you move directly from S2 to F2, or you go via S1, F1 some n number of times for n greater than equal to 0, the word on which this run occurs belongs to L1 language of N1 star. Okay, and this proves the case. So I hope you will be able to study this and check this proof. But what we have managed to do is actually prove that these two languages are equal. So we have done, you know, two both way. The left hand side is a subset of right hand side, and the right hand side is a subset of left hand side, and hence they are equal. That is what we have proved. So this construction lets you do the Kleene closure of a regular language. Given an automaton for a language, we can construct automaton for its Kleene closure. Okay. Is this clear? This is going to be an important construction. Okay, it gives us ability to repeat a certain language arbitrary number of times, 0 times, 1 times, 2 times, 3 times. That is what these iterations are. Repeat the words of the language 0 time, 1 time, 2 times, 3 times, you know, and then you get A star. So that is the Kleene closure operation. Kleene was a very, I think one E is missing. It is actually written Kleene. Kleene closure. Kleene was a very famous logician. You know, he has made many contributions to logic and mathematics, and he came up with this operation on languages. And then one very important theorem is going to be proved, which we will see perhaps in 2 classes from 9. So I hope this Kleene closure is clear to you. We saw one example of this Kleene closure last time, right? Recall how Kleene, this star operation is useful, in defining this. Remember, what was a sentence? We were defining a sentence was defined as what? It was actually a noun phrase followed by a verb phrase followed by a noun phrase. There may be other kinds of sentences. This is one kind of sentence. So example of this is what? The big bad wolf okay. So this is what I call as the noun phrase, and then I have quickly ate. This is something that matches with verb phrase. So verb phrase is a language, and quickly ate is a let us say a sub phrase or a word which belongs to the verb phrase. This big bad wolf is a word which belongs to noun phrase. And we can say here little girl. This is also a noun phrase, right? And what is a noun phrase? We can say noun phrase can be defined as what? An article how do you spell article? I have now forgotten. Is this correct in English? Article or it's CLE? Okay. Article which is followed by some adjective. And how many repetitions of adjective allowed? Here there are 2. Big bad wolf, right? But it could be big bad brown wolf, So we have an arbitrary number of repetitions of adjective followed by a noun. So you see, we can construct this noun phrase by catenating an article which is a, and, the, followed by some arbitrary number of repetitions of adjectives, 0 or more. This is the Kleene's operation start, followed by a noun, So this is going to give you the subject phrase. This is going to give you the verb phrase, and then it's going to give you the object phrase, which is also a noun phrase, where again there will be an adjective. Article is optional. So here we should say somehow this article is optional, right? So I will have to have some notation which will say optionally an article, right? Because here I have no article. Okay, so we'll see how to define patterns like this maybe in today's class or the next class. But here is a use of Kleene closure, and many things in our daily use require arbitrary repetitions. After all, what is an integer? An integer is optionally a plus or a minus sign, right? So I will write this thing being optional by putting a 0 over it, followed by what? I have a digit, and I have 0 or more repetitions of a digit, but I should at least have 1 digit, right? So this is the last digit, and what I have is an integer will have the following form. There will be an optional plus or minus sign. Then there will be arbitrary number of repetitions of a digit followed by 1 digit, because my integer should have at least 1 digit. So this is the last digit, and these are digits before the last. So you can see the use of Kleene closure in this, and it's a very important operation on when you are trying to define patterns of occurrences of symbols, in natural things. And this is the kind of automaton which will recognize that Kleene closure of some sort of things being repeated. Okay, so I hope I have motivated Kleene closure for you. I'll do one last operation on languages, which is the reverse of a language. But first we will talk about reverse of a word. So given a word X, reverse of the word is obtained by reversing the letters of that word. So for example, if you go to ABAB, what you do is the first A which occurs at the start, I put at the end. Okay. And the second letter I put as second last. So I reverse this. I take the mirror image of that. I'm not going to define this formally. It's very clear to you, you know what the reverse of a word is. So reverse of ABAB is BABA. You read it backwards. Instead of reading it left to right, you read it right to left, like in Urdu. Okay. So that is called reverse of a word. It changes the word. It changes this word ABAB into BABA. It takes the mirror image. Is the operation reverse of a word clear? And now we can apply this to a language. Given an arbitrary collection of words over sigma star, reverse of that language is we take every word in the language A and reverse it. So we get a kind of reverse of the language. That is reverse of every word in the language. We get a new language, and that is called reverse of A. So is reverse of A clear to you? So suppose my A was the language. Let me write it in red. My A was the language. Sorry. Where is the eraser? All right. I have ABAB and I have got ABB. So what will be the then? Rev of A will contain what? Can anybody tell me? What will be the reverse of this language A? Please type in the chat.
BABA and BBA.
BABA and BBA. Okay. Why? Because we took this ABAB and reversed it and we got BABA. Then we took this ABB and reversed it and we got BAA. Right? So this is simple. I think there is not much to see here. Next, you know, our theorem is that regular languages are closed under reverse. What do we, when we say something like this, what do we mean? We have shown regular languages are closed under union, intersection, catenation, even Kleene closure, right? So what kind of theorem did we prove in order to show this?
If there is an epsilon NFA accepting A as a language, then we can construct an epsilon NFA which accepts reverse of A.
Right. So how will we do that? Correct.
You can just reverse all the arrows and take the
so
start
given
and
an
final
epsilon
state.
NFA N1, you know, I think this time I don't even need normalized. I'm just saying epsilon NFA. Okay. With set of start states S1, set of final states F1, right? And it's an epsilon NFA. So it may have some epsilon transitions and many non-deterministic transitions also. We can obtain N2 with the same set of states. If the set of states of N1 was Q, I will have the same set of states, same alphabet, you know, silent symbol of course remains the same. What was the set of final states becomes the set of start states now. So all the final states are made the start states and all the start states of N1 are made the final states. Because you're going in the, you know, instead of going from left to right, you are going to go right to left, right? That is what you have to mimic. So you make the whatever final states as start states and start states to final states. And then you do something, we reverse every arrow in the automaton. That is, if there was an arrow going from P to Q on a letter alpha, why do I write alpha? It can be either epsilon or it can be one letter in sigma. So for either it's alpha can either be epsilon or some member of sigma, A, B, C, right? But if you have an arrow like this you have an arrow like Q going to P on alpha in my automaton N1, that is in delta 1, which is, oh sorry, this should be capital delta 1, no? Because these are NFAs, right? In delta 1, then in delta 2, I will have the reverse arrow. It will go from P to Q instead of Q to P. So, right? And so let me give an example. If I had an original automaton like this, sorry, YA1, it should be A. On an A you go here and on a B you go to this final state, right? This is my original automaton N1, right? What does it recognize? Anybody? This automaton recognizes
Words ending with B.
A star B.
A star B.
A star B, exactly. Right? Now what we do is we want to recognize reverse of this. That is something that begins with a B and then there are 0 or more A's, right? But I mean, we could have constructed it ourselves, but the method given here is that the start state becomes the final state becomes the start state. In fact, every start state becomes a final state and every final state becomes a start state. So what we are going to get is same automaton, the designate same set of states, but the final and non-final get exchanged, right? And this becomes, because this was final, this becomes the start state. And my transition, you know, since I was going from this state to itself, if I reverse the source and the destination of the arrow, I get the same arrow. Here the B will go in the other direction, right? Because the arrow is going this way. Now in the reverse automaton N2, you know, I will have this. So this is my reverse automaton by this construction. So is the construction of the reverse automaton clear? Yeah, you just reverse all the arrows and exchange the start and the final states. Okay, and you can see in this example, if you start here, first you will have to have one B in order to accept, and then you will have arbitrary number of A's, right? So it will recognize the language B followed by A star, which is the reverse of this. So this is the way in which we construct the reverse automaton. Now, how do we know that this construction is correct, that it will really recognize the reverse of a language? So what is the proof? So we again show that, you know, every word which is recognized by N1, its reverse will be accepted by N2, and everything that is accepted by N2, its reverse will be in N1, because reverse of reverse gives you back the same word. So we have to prove two-way containment. That is, the language of N1 is contained in language of N2, and the language of N2 is contained in language of N1. So suppose there is a word which is accepted by N1. I mean, N1 is some automaton. Here I have just given an example. What will be there? From some start state S1 of N1, there will be a path which will take me to some final state of N1 called F1, right? Maybe that so from S2 it will take me to some F3, you know, but there is a path from a start state to final state on some word X, right, in N1. That is S1 on X goes to some F1. Here S1 and F1 are some arbitrary start state and final state in N1, right? If this is the case, because we have reversed every arrow and we have made this F1 as the start state and this S1 as a final state, I will have a run F1 on reverse of X, right, to S1 in my reversed automaton. I will just trace that path backwards, and that path is allowed in my N2 because I have reversed every arrow in N2. And remember, this is the initial state of N2, this is the final state of N2. So this reverse of X will be accepted by N2. And similarly, you can argue the other way, you know, that if a word is accepted, reverse of a word is accepted by N2, then that word will be accepted by N1. So this is a simple proof that shows that reverse of the a language is accepted by this reverse automaton, which is obtained by switching final and non-final final states with start states, right, and reversing every arrow. So I think with that we finish what are called closure operations. Let me go back to my initial slide. You know, we have this very powerful set of operations, right? All these operations were there in the languages: union, intersection, complement, catenation, Kleene closure, reversal. And for each case, if the component languages were regular, that is, they were given by some form of NFA or DFA or epsilon NFA, we could construct an NFA or a DFA which will recognize this combined language. And in fact, we can do these operations, you know, in more complex ways also. We can, you know, we can build an automaton which will take A1 union A2 catenated with A3. We can build a complex language by this operation. And in order to, given the automaton N1 for this, N2 for this, and N3 for this, what will we do? We will first take the union automaton of N1 and N2, and then we'll take the catenation of this N1 union N2 automaton with this N3 automaton, and we will get an automaton which will recognize this language. So we can do these operations, use them, many times to get a complex expressions of some form, and we can actually construct an automaton, an epsilon NFA, which will recognize it. And that epsilon NFA can be converted into a DFA by subset construction, and that can be implemented in a digital circuit or using your C program. So this is how you will be able to recognize complex languages. We'll see this very much in the subsequent part of the lecture. Okay, so you see there are these operations, and regular languages are nice. They are closed under all of these operations. Firstly, the basic set theoretic operations of union, intersection, complement. It's also closed under set difference. So let me add a page after other operations. We have shown closure under all these operations, right? By construction. Now by leveraging them, you can also show the following thing. What is set difference? A minus B. Does anybody know the definition? It's the set of all words. Such that X belongs to A and X does not belong to B. That is, from A subtract all those words which are in B. This is called set difference operator. You will find this in set theory. Now my claim is regular languages are closed under set difference. Closed under set difference. Can anybody see why? You can directly give given automaton for A and B. You can directly construct an automaton which will recognize only those words which are in A but not in B. Right? For example, you can take product of automaton of A and B and only accept those words which are in accepting, if these are DFAs, then accept those words which are accepted by the A automaton but are rejected by the B automaton. So there are many ways of directly constructing this, but we will actually reduce this difference operation to something. So what is A minus B? That is A intersection complement of B. What is this expression? This is same as A minus B. Does anybody do this? By Venn diagram you can see this. What are all those words which are in A which are not in B? You take all the words which are not in B and take their intersection with A. You will get all those words which are in A but not in B, right? Now we already know, given an automaton for B, how to construct an automaton for complement of B, right? So N1 for A and N2 for B. We can construct an automaton for A minus B. N3 for A minus B is given by, how is this given by? What you do is you first take complement automaton of N2, which will give me the complement of B. Then I will take product. Remember, product was doing the intersection, right, of N1 with complement of N2. So first you construct complement of N2, then you take N1 and take product of this automaton, which will recognize the intersection. And this complex expression, you first have to take complement of N2, whatever resulting automaton comes, take the product of that with N1, that will give you the set difference. So using these existing operations, we are able to show closure under many other operations. You just have to use identities like this, right? So you can show closure of regular languages under many other interesting operations, like this set difference. There is also an operation called prefix. Ref of what? Okay, so let me define prefix operation between two words. And the idea is that AB is a prefix. I'll write this as subscript P, AB, AB. Why? Because you can delete some part from the end of this word and you can obtain this word. So this word is a prefix of this word, right? In general, epsilon is a prefix of every word X, right? Because you can delete everything in X and you will get the empty word, right? Got it? And of course, a word has got many prefixes, right? So given a language A, I define, okay, let me write properly. Given A, sorry, why am I writing like that? A subset of sigma star, define prefix language of A, which is set of all prefixes of words in A. So all X belonging to sigma star such that X is a prefix of Y for some Y belonging to A. So take a word in A, take all its prefixes and add them, and do this for every word, and you get this prefix language of A. So let's try to do BA and ABB, right? What will be the pref of this? Anybody can start telling me what are the kind of words which will be there. Of course, epsilon will be there, right? Now we start taking increasingly the prefixes of this. So B will be there, BA will be there, BAB will be there, and the word is also a prefix of itself. We will define prefix like this. So word is a prefix of itself. It is not a proper prefix of itself, but it's a prefix of itself. So for BA we get this 5 prefixes. And similarly for ABB, what we will get? Epsilon is already there. Then we will get A, then we will get AB, and we will get ABB. So this is the prefix of this, right? So is the notion of prefix of a language clear to you? Yeah? Clear. Regular languages are closed under prefix, which means what? If you're given an NFA recognizing language A, then you can construct an NFA N2 which will recognize the prefix of that language. And don't do this by reduction to the existing operators, directly give an automaton construction for this. So I'm not going to give this today. I'm going to leave this as homework. So try to imagine what automaton will recognize prefix language of an automaton.
We can basically make all the states as final states, right?
Just try it out on a couple of examples. You are in the right direction, but that is not the answer. So I think it is best you think about this, and then we will find some way by which you can tell me your answers. Okay? But think about it. This is a thinking question. It's not very difficult, but it will get you into this mode of, what kind of surgery you want to do on the original automaton to generate a new automaton, which will do this thing. So this is transforming one automaton into another. Just as you will transform one digital circuit into another to do some other job, right? So think along this. And there are many, many other operations under which regular languages are closed. Okay? Fine. So I have finished this topic of regular, closure under various operations of regular languages. Now what we want to do is one last topic to do with these automata before we move to some other things, and these are called decision problems. So, you can construct various kinds of automata, epsilon automaton that is required. You can also combine these automata using operations which will give you union or intersection, and you can construct very complicated automata. In fact, it is found that there is a systematic way of constructing a deterministic finite automaton for every digital circuit. Okay? So, your Pentium chip will be equivalent to a very large finite state automaton. And you can construct sort of model the behavior of these circuits, in terms of automata. What are the kind of states which arise in that digital circuit can be explored by building its automaton and exploring what are the kind of states or sequences of letters which are accepted by that automaton. So analysis of this automata becomes very, very important. And for analyzing behaviors of many finite state systems like digital circuits or some sort of relay based interlocking mechanisms, you will build a finite state automaton model and analyze it. And what are the kind of analysis you want to do on this automata? We showed you how to construct complicated automata by using these closure operations. But now we are asking some analysis questions, right? These are also called decision problems, right? And one decision problem is what is called membership problem. That is, you are given an NFA n. We can also consider epsilon NFA, but for simplicity, let us consider an NFA. And a word in sigma star. We can ask if the word X is accepted by that NFA or not. This is one question we want to ask. Now, this was easy, right? If I give you an NFA and if I give you a word, you know how to find out whether that word belongs to the language or not. But we want a computer algorithm to do this. And why is this? We want to apply this decision problem. So we want to find algorithms, computer algorithms to solve these problems, which can be applied to very large automata. Maybe a million states, maybe a billion states, and the word itself is very large. So, for example, you could have an automaton which has, let's say 100 flip-flops in it, a digital circuit with 100 flip-flops in it. So each flip-flop will have either 0 as a value or 1 as a value. So number of states of such a circuit is 2 raised to 100. Now, imagine this automaton has got 2 raised to 100 states. It will take some input. So here we have a circuit which takes one input, one Boolean input, which can be 0 or 1 in clock cycle, and it has got, let's say 100 flip-flops. It's a module, it's a counter modulo 2 raised to 100. So it will cycle through these all possible values of these flip-flops and give you some value. Now, what will happen is, and you want to know whether a given sequence, of bits which come as the input to it, 0, 1, 0, 0, 1, is this accepted by my circuit or not? Does my circuit go into some good state at the end of this sequence? That is the membership problem. So, membership problem is very, very useful in order to understand how our model of finite state system works, right? And that is one of the problems that we want to solve. So imagine that your automaton is, let's say, 1 million states long. Your word that you are trying to explore is, let's say, 10,000 letters long, and you want to check whether that word is accepted by the automaton or not. How do we do it? What are the methods for this? This is a question which has a lot of use in, let us say, simulation and testing of digital circuits. Okay, so membership problem is one problem to be solved, and we want to solve it by a computer algorithm where we will represent that automaton, in computer memory in some way. We will give that word to the computer, and then the computer will analyze and tell us whether the word belongs to this or not. This is not a very difficult problem. We already know how to solve it, but I'll show you the solution. But let's see the range of problems that we want to analyze, right? Another problem you want to check is non-emptiness problem. That is, at least there is some word that the circuit, that my automaton accepts. Sometimes automata are constructed using these language operations. So for example, I can have a language L1, which says all words of the form A star B, right? And I will have another language L2 of the form B star A, right? And then I say, okay, I have constructed this language L1 intersection L2 by taking the product, right? So I can easily build an automaton for L1. I can easily build an automaton for L2, and I'm saying both these constraints should be satisfied. So I take the product, But then you know there is no word which will belong to both of these languages, because all words should end in a B and here they should end in an A. So there cannot be any word which simultaneously ends in a B and also ends in an A. And I will get a language which is empty. I've got contradictory requirements L1 and L2. So how to know whether those component automata are representing contradictory requirements? We check if its language is empty. Okay, that is what we will be doing. Okay, so I have motivated checking for emptiness or non-emptiness of a language of finite automaton, right? And this is an important question. We'll see that this operation is also useful in many other cases. A more important question is that of language equivalence. So suppose you are given two NFAs, N1 and N2. We want to determine whether it represents the same language or not. Okay. And this can be, one can be a very complicated automaton, other can be a simple automaton. And we want to check if they are both doing the same job, or, you know, so we optimized N1 to get N2, but we want to be sure that the languages remain same. So here is an example. You know, I have this, I gave this example before also. Here was an automaton on a single letter alphabet, which was recognizing all sequences of A's where number of A's is even. And then I had a more complicated automaton. Remember this? You had this cycle of 4. Here they happen to be both DFAs. Okay, and the alphabet is a single letter. So this is a very simple case. But these two are different automata, but they have the same language. But how do I know they have the same language? So I need some method of checking that, you know, the two automata are language equivalent, right? That is, they have the same language. And this is important because every digital circuit can be reduced to a finite automaton. Many other things we will see can be converted to finite automata. And then when we optimize a digital circuit, you know, somehow we want to obtain an automaton which is equivalent to this. See, if it was combinational logic, we would check equivalence of combinational logic. We will use methods like Carnot maps. For those who are in electrical engineering, you will know that we optimize combinational circuits by producing smaller circuits, you know, and somehow we have to show that these two are combinationally equivalent. For all inputs, they give the same output. Similarly, for two sequential circuits, to check that they do the same job, what the easiest method is to convert both sequential circuits to their automata. You know, maybe one will give you this automaton, one will give you this automaton. And then you know, they don't look the same, but somehow we have to check that they have the same language. So this is a very useful operation. And actually, you know, if you can do this well, I'll tell you a story at the end of this slide. You know, but if you can do these things well, you can earn a lot of money. You know, these are considered some of the very useful but difficult problems, you know, for very large automata. And there has been intense research in. Now, okay, before that, you know, to check whether two languages are equivalent, we can say that one is a subset of other and the other is the subset of the first one. So you can reduce this equivalence checking to checking subsets, right? Two such checks will have to be made. So I think there is no surprise here, right? So we can reduce language equivalence to checking language inclusion. That is the language of N1 included in the language of N2? And the language of N2 is also included in the language of N1. So compared to language inclusion, there is a more basic language equivalence. There is a more basic operation called language containment or language inclusion, where given two NFAs N1 and N2, of course, everything is over same alphabet. We are checking whether the language of N1 is a subset of language of N2. That is, every word accepted by N1 is accepted by N2, right? Now, these are the kind of operations that you want to do on large automata. And if you can do this, you know, a lot of problems in real life can be solved. For example, every electronic circuit design tool, no, produced by companies like Mentor Graphics or Cadence or Synopsys, you know, have got modules which will, you know, for for analyzing the circuits for their correctness, which will require these operations to be done. And they are very interested in doing these operations on the automata generated from circuits, but they want to do it efficiently on very large automata with, you know, hundreds of thousands or million states. Okay. And so if you can produce algorithms to solve these problems on large automata, it is of great interest in practice. So how do we solve these problems? This is what we are going to look at in the rest of the class. I am just going to do this, you know, a little fast because I think it requires certain background in graph algorithms, but let's do it. So first is this membership problem. Okay, we will take all these three problems one by one, and we see some method by which computer can solve this problem. So given an NFA n and a word, we want to determine whether that word is accepted by the automaton or not. Right? This is the problem. And how do we solve it? You know, we already saw one method to solve this. So let me add a page. And let me give you a candidate automaton. Okay, I think we had called this 0, 1 before. But this is my automaton and it's a non-deterministic automaton. Do you agree? Because from this state S1, S2 and S3, you know, and from S3 you can't go anywhere, right? And this is my unique start state. What does this recognize? Second last letter is an A, right? Now, how do we know whether the word ABA is accepted by this automaton or not? We saw one method. We had this mathematical technique, that is, you know, we computed delta hat from S1, right, on ABA, and we checked if on, oh, sorry, no comma there. Pen is a little bit confusing. ABA, and then we checked whether its intersection with the set of final states, that is S3, is non-empty, right? That was our check. Recall this method. But basically, intuitively, what are we doing? We start our, we draw a kind of computation tree of executions which are possible under the word ABA. We simulate this NFA, all possible runs of this NFA, you know, simultaneously. So the first letter is an A. From S1 on an A, where all can you go? You can go to either S1 or you can go to S2, right? So this is the frontier that I have after letter A. Agreed? And then after this, each of these states, if a B occurs, you know, from S1 on a B, I have to stay in S1. From S2 on a B, I go to S3, right? So the new frontier after the word AB is this. So I start with my initial frontier as S1, and then on an A, I go to the frontier S1, S2. And then on a B, I go to frontier S1, S3. And then on another A, what will happen? Can somebody tell me what will happen on another A? On a letter A, oops, I've got the wrong color. I'm sorry. Yeah. On a letter A, I will go to S1, S2, and S3 on an A will not go anywhere. This will die. So the new frontier I've got is S1, S2, right? So here on another A, I will go to S1, S2, right? And in each step of computation, what will I do? I will take every state in the previous frontier. On that letter, where all it can go, I will add to the next frontier, and I will do this. I will scan over this set one by one. This set is given as a list. In the computer, I will represent this set in my computer memory. Then on a letter, I will pick up each of this state and find out which are the states to which I go, and I add it to the next frontier. So I will always compute next frontier from the previous frontier. Okay. And I will successively compute this till I get the last frontier. And then I check whether this intersection, my set of final states, is non-empty. That is, there is some final state which is in this set. right? In that case, the word is accepted, right? This is the algorithm. This algorithm can be implemented in computer. So you initialize the frontier to the set of start states. This is my initial frontier. You scan the word from left to right, one letter at a time, and do the following on every letter. For the current letter, you calculate the new frontier as old frontier on letter A, where all does it take you, right? And this you can do, there will be certain amount of time taken to do this. And at the end, you will have some frontier. You check whether that frontier intersection final state is non-empty. And how is what, right? So this algorithm is something that we have been doing before, but this can be implemented in computer memory. Now, how much time will it take? Well, you will have to do this simulation for as many steps as the length of the word. And at each stage, you will have some subset of states in your frontier, and each of those states will give rise to a subset of states. So potentially you will have, something proportional to the number of states, in your frontier. And so at each state, your upper bound on the algorithm will be the length of the word multiplied by number of states. This is roughly what we call in computer science as the big O notation. And it gives you that some constant of this expression is roughly the amount of time that you will take to check membership, right? So this is nothing but the simulation method for the NFA. Okay, and we can determine whether a word belongs to is accepted by an NFA or not. If this was a DFA, then if this was a DFA, then you will not get multiple runs. You will get a unique run, and it's very easy to implement. You just check which state you go to. You just store the current state and keep updating it, right? So you just simulate the DFA. In case of NFA, you will have to keep these frontiers, the set of states which are reachable. Okay. Is this clear to you? This membership problem? Okay. What about non-emptiness? See, basically what is membership? If I want to find out whether a word ABA belongs to it or not, in order to show that a word like, let us say, ABA belongs to my language, what would I do? I have to show a path from some start state to some final state on the word ABA. Right, that is what I have to show. And since it's non-deterministic, there can be many paths on this word. I have to show one path which will take me there, and I can show it like this. On A and a B, I stay there. On an A followed by B, I just take this loop twice. Then on an A, I go here, and then on another A, I go here. Right, so I take this path: A, B, A, and A. And till I have shown such a path, I know that the word is accepted. And what I am doing is I am symbolically searching for such a path simultaneously. Okay, that's what I'm doing. So basically a word is accepted by an NFA if there's a path on that word from the start state to the final state. Now the question we are asking is slightly different in the next problem. We are checking whether this automaton accepts at least one word or not. That is what we are asking. Now, does this automaton accept at least one word? Is its language non-empty? Can anybody tell me? Does this automaton have a non-empty language? Yes or no?
Yes.
Why?
AA is accepted.
Right. So how do we search? We actually have to search for some path starting from some start state to some final state, right? And on that path, whatever letters occur will be the word which will be accepted by the automaton, right? But we have to only check whether its language is empty or non-empty. So we even ignore the letters. We just search for one path from a start state to a final state. Okay. So we treat this automaton as a graph, and in the graph from one of the start states, you have to check whether there is a path to one of the final states, right? This is called the ST connectivity problem. S is the start state, T is the final state, and are they connected by these directed edges, right? This computer science people will call it connectivity problem, okay? And it's a very well studied problem, given a graph, whether you can reach some node T from some starting node S, following the arrows that are given, is the question, right? And there are actually many standard algorithms. Basically, we have to search for a path from a start state to final state. And this search can be done systematically. There are many search methods. There is a method called breadth first search. There is a method called depth first search. Now, how many of you have not heard of these terms? Please type in the chat saying no, so that I know whether I have to give you some introduction. You won't be asked questions on these methods in the exam, but there are algorithms called breadth first search or depth first search, which can basically check if there is a path. Okay, I got one no, two no. That's fine. Just getting a, I don't have a poll facility yet. So, okay. So I'll give you an idea of this breadth first search algorithm next time, because we are running out of time. But yes, I'll maybe set up a poll and you can answer there. So there are these methods which will check whether there's a path going from a start state to a final state. Okay. And the amount of time that such a method will take will be, if my automaton has, if I have got Q states plus number of transitions, let E denote the arrows in my graph, the edges in my graph, the number of transitions. So if I add number of states and number of edges, the time taken to find out whether there is a path from a start state to final state will take roughly this much time. Okay, but we will see this algorithm little bit next time. Okay, let me finish with the last problem, the language containment. And if you can solve language containment, you can do subset. You can do equality of two languages. So do two automata recognize the same language? I want to check that. So given automaton NFA N1 and an automaton N2, what I want to check is language of N1 subset of language of N2. For that, I make use of the following identity. By Venn diagram, you can check that set A is a subset of set B if and only if you take the complement of B, things which are not in B, take its intersection with A, and if this set turns out to be empty, then you are guaranteed that this is the case, and if this turns out to be non-empty, then you are guaranteed that this is not the case. Why is that? You got set of elements A, you got set of elements B, and not of B will contain, all these things which are outside, things like this, right? And if A intersection not of B will contain all of these things, they have something in it, then certainly B is not a subset of A. A is not a subset of B, because there are some things, which are in not B, which are included in A. So I think this identity is not difficult for you to see by Venn diagram. And I'll leave you to check that this identity is true. Now we apply this to these languages, which are also sets. So in order to check that language of N1 is a subset of language of N2, what do we do? First, we have to, for N2, we have to find its complement. So we first construct an automaton for complement of N2. And then to find the intersection of that with language of N1, I take the product of automaton N1 with this complemented automaton N2. That will recognize the emptiness. And then this automaton that I get, I check if its language is non-empty or empty. It should be empty. In that case only, I have this thing as true. If it turns out to be non-empty, this is false. So by using this previous operation of non-emptiness, I can check whether L1 is a subset of N2, right? So you see this reduction. And how do we do complementation of NFA? We first determinize N2, because we can only complement a deterministic automaton, and then we complement that automaton, right? So actually this complement is determinized followed by complementing the deterministic automaton. So these are the operations that are to be done in order to check that one automaton is a language of one automaton is a subset of another automaton. And once you can do language containment, you can check for equality. So this is the method which is used to check whether two sequential circuits have the same language, whether an optimized form of a sequential automata which is using less flip-flops, fewer gates, is it giving the same result after arbitrary number of cycles for arbitrary inputs? Is it the case that the two circuits are behaving in the same way? We can check using methods like this. And these large electronic design tool companies, they are implementing these methods using very sophisticated methods. I have shown you a simple method. but there has been, 20 years of research on solving this problem efficiently using computer algorithms, and these are problems which are of interest, and applied to very large automata. Okay, so I have shown you three problems: membership, non-emptiness, and language containment. And language containment can solve language equality, right? Of this, non-emptiness is done using what are called breadth first search or depth first search, and I'll give you a brief idea of that next time. But not only do you know how to construct very complicated automata from very simple automata using all those closure operations, of intersection and union, and let's go back to that slide. I'm sorry, here, using all these operations. But for the resulting complex automata, you can also check, solve the analysis problem, the decision problems. So this ability you have, and there are well-known tools and libraries available which you can directly use and check these problems. So you don't even have, these methods have already been implemented in some well-known libraries, and today we have the ability to solve these problems, at some scale. So I hope you got some flavor of, how to build complex automata and how to analyze them. That is what we have done today. Okay, I think I should close with that. I've slightly overshot my time. So I think.
Sir?
Yes.
Just an idea about the closure and the prefix. So instead of making every state as a final state, we should only make those states as final states.
I think I won't comment now. I told you right away that you are thinking along the right lines. If you want your solution to be checked, please mail it on, the Q&A, not Q&A. Let's see. How do we do it? We'll give you instructions on how you can submit your outline answer. You don't have to give the full construction. You can give your idea. Maybe you can mail it to us on Moodle. Maybe we'll set up a way by which you can give us the answer, and then we'll give you feedback. And we'll discuss this prefix in a tutorial. Okay? But let me tell you, you are getting close.
Okay, sir. Yes, sir.
Who was talking?
Me, sure.
Okay, sure. Okay, but all of you try this. I think it's an interesting thinking question. And it will give you a chance to respond on Moodle with your idea. You don't have to do the full construction. Just give me an idea. Of course, if you do the full construction and do the proof, that is like, the best that you can do, right? Because sometimes ideas can be wrong in some corner cases. So it's best to actually formally prove that, your idea is correct. Okay, so thank you. Yeah. Any other question? If there are no questions, I'll stop recording. And you can also